was talking about earthquakes along the subduction interface. So Alaska has the Aleutian subduction zone here. A lot of studies have been done along these islands out here, looking at land level changes to determine earthquake histories. However, I'll be talking about reverse faults. So the Chugach St. Elias Mountains here are really in the Coast Range. The Castle Mountain Fault here is sort of in the Forearc Basin. And then there's a series of reverse and thrust faults in the Alaska Range, responsible for growing the Alaska Range. Mount Denali is 26,000 feet. So different environments of reverse and thrust faults. And I will mention that thrust faults usually have a shallow dip, but in the shallow subsurface, they tend to steepen up and basically affect the geomorphology as reverse faults. So let me see. So I'm just going to go through a couple of these faults and just show some of the evidence of what we know. So starting out in the Forearc Basin, the Castle Mountain Fault extends right here, just north of Anchorage. And I'll be talking about showing some LiDAR within this box right here in the Susitna Basin. The fault, this photo in the middle, extends east-west and is really prominent. It was early on thought to be a strike slip fault because it was so straight, but the deciduous trees grow on the uplifted side and the black spruce grow on the marshy kind of downdrop side. Industry seismic lines over here on the upper right show a steeply dipping fault with back thrusts, and about a 4-kilometer wide anticline just north of the fault, and also paleoseismic trenches in this marshland out here in the Susitna Basin has also identified reverse faults and folded peat marsh stratigraphy. So the upper picture shows just the forest, or it's just a satellite image, and the picture that shows the nice linear trace is right about here, but a lot of trees and hard to find things. So we acquired some LiDAR in this area and use it to map the quaternary geology, which is shown on the bottom. So the purple is a glacial moraine, and the various pinks and olives are sand plains, basically glacial outwash plains. So similar to Seattle, which you'll see in your homework, is the area was incredibly glaciated and buzzsawed down. So you're only really seeing the last, the Holocene record pretty much. Okay. Here's what it looks like in the field. So some of these features that you can interpret from imagery that you'll do in your homework, but in the field, it's a nice rounded scarps, sometimes over steepened at the base, but just nice rounded scarps all the way through the Susitna Basin. So here's some close-ups of this LiDAR. And here's a hillshade here on the lower left. And what you can notice here is trending east-west is this sort of shadowed south-facing fold scarp with left stepping and echelon scarp superimposed on the face of that scarp. They show up nicely in this slope map as well. And then also north of the scarp, there's these sort of an echelon stepping grobens shown by these kind of light yellow highlight on the scarps, north facing and south facing. So that's another feature typical of reverse faults, is this sort of hanging wall deformation or flexural slip faults in the hanging wall. So as an anticline builds above the fault, you have extension in the hanging wall. And then on the right is just an interpretation of some of those scarps shown in red. So here's just a couple more examples. This is 1 to 16,000 scale images. Here's the LiDAR, nice south-facing scarp shown as this dark tone coming across. And then typical also are a lot of landslides along reverse faults. So it kind of obscures the trace of the fault around here. Whoops, sorry. And that shows up nicely in the slope map as well. And then here's the interpretation of that. And then down below, again, just showing the thickness of the forest and how hard it is to interpret this stuff in the forested area without LiDAR. But here's the fault trending across a floodplain of the Little Susitna River and the interpretation there.
Richard,
Sorry, go ahead.
I had a quick question. So when you are trying to do fault traces and there's a superficial deformation, does that prevent you from inferring where the fault traces are going to be?
We look for places where you can see the trace of the fault, and then say in the middle of this photo, places where you don't see it at all. So that would be kind of an area where you might dot it as being concealed. So this is a floodplain that would be younger than the last rupture. So we're just looking for the evidence of geomorphic features and then drawing them.
Okay.
Does that answer your question?
Yes.
Yeah, and this is Chris. My slides will focus more on geomorphic change along fault scarps and how you might consider that during your mapping, like what processes have happened since the last earthquake that could locally obscure the fault trace.
Okay, great. Okay, so then here is some close-up views of the LiDAR. This is down to 1 to 3,000 scale. So again, on the left here, the left image you see is sort of fold scarp here, and then also some scarps that sort of project off to the north. Similar in the middle here, there's some stepping traces here, and then a subtle trace up above to the north as well, so in the hanging wall. Another thing to notice here is these channel margins are basically been abandoned since the last glaciation due to isostatic uplift. So these are abandoned channels, and they show basically no lateral displacement across the margin of the channels here. So primarily vertical deformation with this south-facing scarp. I have to keep moving the zoom thing out of the way so I can see what's going on. And then in the right, here's some stepping traces again. So some left stepping and echelon scarps across the face of the fold scarp, which suggests maybe a component of lateral deformation. And then on the bottom here, there's just some schematic profiles across the scarp, just showing the general scarp morphology. So either some back thrusts or multiple parallel reverse faults coming to the surface. So multiple breaks across the scarp. Let me do it on time. So here's a couple of oblique views. So with your LiDAR, you can enter it in QGIS or ArcGIS and rotate things around. So this is looking to the east, and this allows us to see sort of a small scarp in the youthful floodplain of the Susitna River, a kind of a larger scarp in sort of the early Holocene deposits. And then you can also see by projecting down strike the kind of bend in the fault trace here. And then on the right, here's just two other sort of oblique views of images that I've shown before, showing the left stepping and echelon fractures across the fold scarp. Back here, you can see these grobens. And then here's a landslide again on the lower left here, and a scarp going across. Let's see, there's a few more slides here. Another interesting thing is where you lose trace of the fault scarp. It's not very well expressed here in this part of the middle of the valley here, but you do see a scarp subtly coming in here, and then there's somewhat of a step. So another feature that's typical of reverse faults is areas where there's steps, you may not see a scarp going through, but you'll have a sort of a broader region of folding. So here's a profile drawn down the middle of this zone, and you have about a 1.5 kilometer wide anticline there with no surface expression to speak of, really. So you have to look for that sometimes when characterizing these faults. So I think it's shown you some geomorphology of the Castle Mountain Fault, and a lot of the scarp morphology is really similar to several other earthquakes in the world, the 1980 El Asnam earthquake and the Spitak earthquake, and also really similar morphology to the Osler Fault in New Zealand. Similarities in scarp morphology, hanging wall extension, and some wrinkles in front of the scarp and various echelon scarps. So pretty typical expression of reverse faulting worldwide is seen there. And then I'm almost out of time, but I wanted to touch just briefly here on the Northern Foothills Fold and Thrust Belt. So the Alaska Range is here in the upper map, kind of with the Denali Fault curving along the center of the range, but there's a wide zone of thrust faults and reverse faults on both sides of the range. The Northern Foothills Fold and Thrust Belt, studied in detail by Bemis, shows a bunch of parallel ridges. So there's uplift along these thrust faults, and there's antecedent rivers that cut through the ranges. So the river drainages are older than the uplift, and they've kept pace eroding through those ranges as they've come up. On the right is the structural interpretation of the fold and thrust faults. So you see a lower basal thrust and then some steeper faults coming to the surface. So Bemis mapped these glacial outwash terraces in the Nenana River Valley and showed deformation through time. So the greatest amount of deformation is the Pleistocene Nenana gravels. They show uplift and folding over these faults, and then successively less deformation on younger glacial outwash terraces, but definitely showing active deformation in that zone. And this is what it looks like in the field. On the northernmost thrust, just a big fold scarp. Here's the Park Road fault, which is a back thrust of the system. And I'll just zoom in real quickly on this image on the right. Shows a nice scarp coming across, and then some collapse features or maybe some brabins in the hanging wall. And then it's obscured by landsliding over here. Here's what that looks like in the field. So this image on the right is these big grabins in the hanging wall, and this is a 12-meter scarp. So, and then the last example is the Cathedral Rapids fault, which shows folding. We did some trenching there, and so we show folding. We don't find the fault at all, but folding of flat-lying deposits. Here's what it looks like in LiDAR coming across there. You have a big range front with triangular facets in the upper right. And then further to the east, we have what's called the giant mole track anticline, which shows up really nicely in the DEM, where you have the range front to the south, and then outboard of the range front, you have this mole track anticline where there's folding along a thrust there. And the one interesting thing that was done there by Carver et al. 2010 is they found a graben in this massive anticline, and got at the earthquake history by looking at sediments, colluviums within the graben. And that trench is in this little white box right here, which is in this river cut through the giant mole track. So it just shows up really nicely in the topography and in these photographs, especially right here in the DEM. So that's all I have. Is any questions about those examples?
I have a quick one.
Yeah.
And your in your one photo, how could I tell the difference between the scarps and geomorphic features in the LiDAR slides? So like where you were showing like all the in echelon scarps. Yeah, that slide right there.
This one here?
Oh no, one forward.
This one
Yeah.
here. Well, this is zoomed in really detailed. So you probably want to zoom out a little bit to infer the geomorphology, but you know, you could see like these are river channels coming through here, and they're cut. So there's features that cut across the river channel.
Okay, I see.
See what I mean? So when you zoom out a little bit more, you can see like these are big sand dunes cruising along here, and then there's channels here. You know, so you're just basically interpreting the geomorphology based on the image.
Oh, right.
Can I ask a question, Rich? Just if you could point out, so is there evidence in your research of only a single event here, or is this multiple events, do you think?
Across the Susitna Basin, there's evidence for 2 events. There's one that's basically immediately post-glacial. And so there's places where you do see 2 events, mainly in the western part where there's kind of an older piece of landscape that records it. But a lot of the low-lying flat plains only record 1 event. So Plafker had a trench with an event dated at about 2,500 years. And then we had a trench on the eastern side that has an event just basically immediately post-glacial, like around 11,000, 10,000 years or something like that. So 2 events in the plain, but really 1 event is preserved in many locations.
And so this example, this landscape here is really just showing the 1 rupture, which was a pretty large event across that landscape, right?
Yeah, in a few locations it is recorded. 2 ruptures are recorded, But yeah, mostly that's the effect of one reverse fault rupture in a glacially scoured landscape, which is somewhat similar to the Seattle fault, which had maybe a few, 3 events or something like that, but still a scoured landscape that's showing the post-glacial deformation.
Got it.
I have a question. So your slide prior to your New Zealand slide, you had some anticline that you said you could map. You were saying that the fault scarp is perpendicular to that?
Yeah, so here's the main LiDAR thing. So the map and the fault goes east-west across this whole patch of LiDAR. And so this is just a piece of that. So we've drawn profiles kind of north-south across that east-west trending fault. And again, we don't see a fault scarp per se there, but there is a big anticline showing the deformation in the hanging wall.
And you could tell that from this LiDAR image?
Yeah, well, we mapped the fault scarp up to this area and then found a zone where we couldn't find the fault scarp. So we're like, oh, what's going on? Oh, and then we looked at the map view orientation and noticed that there is a step in the 2 traces. And so somehow the fault is making a bend through there. And so then we started doing profiles to sort of assess how the landscape had been deformed.
Gotcha. Thank you.
Should we have Chris go next? There's no more questions.
Sure, I'll stop sharing my screen.
Yeah, if there's any time at the end, we can also have a few minutes for general questions as well.
Ramon, do you have slides too?
Yes.
Yeah, sorry.
Okay.
On mute. Yeah, I have slides, but you go first, Chris.
Okay, I always feel like you're relegated to the end and then never have enough time, but I can show slides.
I'm happy
I'll go
to
quickly.
defer to you guys.
Okay, let's see here. Okay.